Okay, let's try and start to describe informally what we mean with an anomaly. This is a good place to pause the video and think for yourself. How would you describe what an anomaly actually is? Well, if you try to do that, you might have run into problems because at first glance it seems that there are no real features by which we can describe an anomaly, and that it heavily depends on the application scenario, whether something is anomalous or not. And this is of course true, but maybe also looking at the picture helped you to come up with a description, because if I would ask you what are potential anomalies in this picture, I guess everyone would directly name the red fish as the most likely instance of an anomaly here. And this is because the red fish is of course very different from all the other fish, by color, by size. So looking a bit further or a bit deeper into the image, we can also identify other candidates of potential anomalies. For instance, if you look to the very right, then you see that the blue fish there seem to be like strangely deformed, so making up another like potential anomaly, although it seems that they are not as anomalous as the big red fish. And this is really the essence what we want to describe with an anomaly. There are also several researchers who tried to phrase this in their own words, and we are going to go through a couple of these definitions. So one of the very early ones is Grubbs, 1969, saying that an outlying observation or outlier is one that appears to deviate markedly from all the other members in the sample in which it occurs. Another one, which is very often cited, is the one by Hawkins, saying an outlier is an observation that deviates so much from the other observations as to arouse suspicion that it was generated by a different mechanism. And finally, a slightly newer one by Candola and others, saying that anomalies are patterns in data that do not conform to a well-defined notion of normal behavior. So now that we know what we're looking for, we can see that anomaly detection seems to be a very hard task. As an example, you can imagine that you're a guard patrol at a very crowded beach and you try to identify thieves. Now, looking at the mass of people, you know that it's pretty hard to identify them because you don't know what to look for in the first place. Thieves might even try to look like normal guests on the beach and try to deceive you. And these are exactly the problems that we need to tackle when we want to apply anomaly detection in practical scenarios. Let's talk about the practical relevance of anomaly detection. Anomaly detection has some quite direct applications in numerous industries. I want to present three of them here: predictive maintenance, fraud detection, and intrusion detection. The first being predictive maintenance. In this case, we want to determine the condition of in-service equipment in order to optimize the maintenance cycles. This is pretty intuitive because too frequent inspections will cause unnecessary costs and downtimes, while too infrequent inspections can lead to failures or even breaking of the equipment. Anomaly detection can be very helpful in this case because deviations from normal readings of the sensors might indicate that we have a wear in the system and that we want to run another maintenance cycle. Fraud detection is another very important use case. In this case, we want to identify fraudulent transactions, for instance, on credit cards. Of course, this is meant to prevent criminal activities and to avoid financial or other damages for the involved parties. Again, fraudulent transactions can be identified due to unusual destinations, amounts, or an unusual network topology if we talk about several transactions. Let me tell a personal example how this can happen. A couple of years ago, I was in India for a conference, and of course I was using my credit card there a couple of times, and suddenly it got blocked. After doing a couple of phone calls, I found out that my credit card company found it very unusual that I do transactions in India. This was actually the furthest I traveled by that time. And so the credit card company identified these transactions as anomalous and blocked the card. Of course, back then I was not too happy with this situation, but thinking that the true fraudulent transaction could cause high financial damages to me, I'm of course very happy that the credit card company is rather conservative here. So finally, let's have a look at intrusion detection, an equally important use case. In this case, we want to detect attacks against a network and protect the nodes against unauthorized access. Again, this can be tackled with anomaly detection because intruders often leave unusual footprints such as protocols, ports, the number of packages, the IP, or the duration of the connection. As an example, you might want to shield your ERP system against unauthorized access by intruders. One potential harm could be that an intruder tries to inject fake invoices into your system in order to get paid for services that he did not do. This might seem like a very strange idea, but believe me, that actually happened to rather large German companies, so you really want to be shielded against that. So why is anomaly detection different from other fields of machine learning? First of all, it's very hard to identify anomalies, and therefore we often don't have labels in our dataset. Even if we have labels available, anomalies are by their very nature rarely represented in datasets, and that means that we have to work with high-class imbalances. Finally, we might not even want to restrict our system to anomalies that we have encountered in the past. For instance, consider the scenario where the anomalies are generated by an adversarial, for instance in the credit card fraud case. In this case, the adversarial might change his behavior over time, and we want our systems to cope with that. So that means that the information that is available heavily influences the available techniques. Questions that you should ask yourself when you want to install an anomaly detection system are: is the distribution of the nominal data known? Is there clean data available for training, meaning data without anomalies? Do we have labeled data for evaluation? How large is the proportion of anomalies in our data? And how much noise is in the data? So far, we have defined what an anomaly is on an informal level. We have seen possible applications of anomaly detection. But in order to really develop methods that are able to identify anomalies, we need to come up with a formal description what anomaly is. In this course, we are going to work with the Contamination Framework, which is a very popular framework for defining the anomaly detection task. In this case, we assume that the data comes from a mixture of two distributions, a distribution F0, which generates the nominal data, and a distribution F1, which generates the anomalies. Our data set then comes from the mixture model with relative frequency P of the anomalies. So we can write the overall distribution as 1 minus P F0 plus P times F1. The task of anomaly detection is then to estimate if a given sample which comes from this distribution is actually anomalous or not. Note that we don't have any labels available because we're just drawing all the points from the same distribution D. Looking at this setup, I guess it's pretty apparent that we will need additional assumptions in order to be able to identify anomalies reliably. So typically, one imposes the following assumption. First of all, we assume that the anomalies are few, meaning that the relative frequency P is way larger than 1/2. Second, we want them to be outlying, meaning that the distributions F0 and F1 do not overlap too much. And finally, we want them to be sparse, meaning that F1 is less clustered than F0. Okay, let's try to understand why we need these three assumptions. So first of all, I think few is pretty intuitive. Imagine that we have like really an anomaly frequency of 50%, then our data might really look like something like that. Just really two blobs of data that are not really distinguishable by any features. In these cases, it will be very hard to tell which of these two blobs is actually the anomalous one. So this is a case that we definitely do not want to allow. Secondly, we have the outlying property. In this case, again, we can look at the extreme case that F0 is just the same distribution as F1. In this case, we really have no chance of distinguishing anything because each of the two distributions can generate every point equally likely. And since we know that the relative frequency of outliers will probably be very low, so it's probably like from a Bayesian perspective, best to always predict nominal, which of course is a case that we also want to exclude. And finally, why do we want to have them sparse? Again, in this case, we can consider nominal distributions where the distribution itself clusters into smaller clusters. And then we will get into a problem if also our anomalous data kind of builds such a neat cluster. If our nominal data looks something like that, and I kind of come and add my anomalous data, which just looks like another cluster in this distribution, then again, we have no chance of identifying it. And these are the reasons why we need these three assumptions. The natural question is now, is this the silver bullet to tackle all anomaly detection scenarios? And I directly give you a clear no towards this. Why is that? First of all, maybe the situation is not as bad as we described it in the contamination framework. Maybe we have data from which we know that it's clean, meaning that it does not contain any anomalies. We can, of course, use this for training and make the problem a little bit more benign. But it can also be less benign than the contamination framework. A very important case is where we don't really have a well-defined distribution for the anomalies. This is, for instance, the case if we're talking about adversarial scenarios. In this case, our adversary might want to try to make his moves as similar to the nominal ones as possible. And then, of course, we will see some distribution shift over time. The adversarial might adapt even to our systems that we have in place. So we will not be able to assume that the anomaly distribution is fixed over time. And finally, usually not be so fortunate to find all these three assumptions fully fulfilled. It's often that the three assumptions of few, sparse, and different are fulfilled to certain degrees, and the degree to which they are fulfilled heavily also influences which kind of techniques we want to use. In extreme cases, this might even be that some of these are false, as we just explained with the adversarial scenario. Anomaly detection does not only demand special techniques for training, but also for evaluation. This can easily be seen if we consider the case that we only have 1% of anomalies in our data. In this case, deploying an anomaly detection system that always predicts nominal will already give us 99% accuracy, which already shows that in such cases, accuracy might not be a good metric to evaluate the system. Better metrics are precision, recall, and the F1 scores. In order to understand them, let's revisit the confusion matrix. Given a test set of n samples, we can apply our anomaly detection system and compare the resulting labels with the true labels. We then obtain 4 possibilities, namely that we have predicted nominal, and actually also have a nominal point, which we call true negative. We have predicted nominal, but actually have an anomaly, which we call false negative. We have a predicted anomaly and actually have a nominal point, which we call false positive. And we have predicted anomaly and actually have an anomaly, which finally is true positive. The measures that we've talked about earlier all use these numbers and combine them in different ways to highlight different aspects of the system. So first of all, the precision is defined as the true positives divided by the sum of true positives and false positives, which estimates the probability that an observation is anomalous given that the system predicted it to be. On the other hand, we have the recall, which is defined as the true positives divided by the sum of true positives and false negatives, which estimates the probability that an observation will be detected as anomalous given that it really is. And finally, the F1 score, with a slightly more complicated formula. It's 2 times the precision times the recall divided by the sum of precision and recall, which is the harmonic mean of precision and recall. It helps to combine these 2 metrics into a single one. In order to evaluate the measures that we've just talked about, we would assume that our system gives us a hard decision, meaning a 1 if the point is predicted to be anomalous and a 0 if it's predicted to be nominal. However, most anomaly detection systems actually provide an anomaly score, where higher values mean more anomalous, and it's up to us to decide which degree of anomalousness we want to detect. So that means that for every possible threshold that we choose, we get other values for precision, recall, and F1, and then we can try to find the optimal threshold. One way of doing that is the precision recall curve, which plots the pairs recall for a given threshold against the precision for a given threshold, and we do that for all the scores that we got in our data set. So you see an example of a precision recall curve on the right side. You can see the optimal value would be on the upper right side, being that precision and recall are 1. But as you can also see, that as the threshold gets larger, we usually decrease the precision but increase the recall, and it's up to us to really find the optimal point here. Another important curve is the so-called receiver operator characteristics, or ROC curve, which plots the true positive rate for a given threshold against the false positive rate for a given threshold, where the true positive rate is defined as the number of true positives divided by the sum of true positives and false negatives, and the false positive rate is the number of false positives divided by the sum of false positives and true negatives. An example of a ROC curve is on the left picture. Here in the ROC curve, the optimal point is on the upper left corner, and again we can try to identify the threshold which leads us closest to this point. Finally, let me also mention that it's possible to assess the overall quality of the anomaly detection system using the ROC curve and the PR curve without the need of choosing a particular threshold. We do that by computing the area under the curves. Remember that the optimal point for the ROC curve was the upper left corner, and the optimal point for the PR curve was the upper right corner. In both cases, a perfect classifier would produce an area of 1, and the lower the number is in general, the worse the classifier gets. Alright, I think by now we're ready to have a look at our first simple anomaly detection technique. In order to develop it, let's have a look at what would happen if you would already know what the distribution of the nominal data is. Say it's given by a density function. In this case, we could simply take the negative log as of the density function, which is also known as the surprise, and measure how surprised we would be if we would draw a sample like that from the given nominal distribution. However, this is often a case that we cannot expect to have. Usually we don't have an idea how the nominal data is distributed, and of course estimating the distribution of the data is a hard task on its own. Slightly simpler is estimating the covariance and the mean of a distribution. In this case, we can take the following distance, which is called Mahalanobis distance, in order to evaluate whether a point is anomalous or not. The Mahalanobis distance takes the following shape. So you take the difference of your observation with the mean that you've estimated, and then you take this quadratic form with the inverse of the covariance matrix and take the square root of that. This implicitly measures distances according to a unimodally centered distribution. So we really measure the distance in terms of standard deviations of a distribution that the distribution has in the space. Meaning that it of course has only a restricted applicability, only if we have really good reasons to believe that our data distribution is really unimodally centered around the mean. If this is not the case, there is a simple extension of this where we can fix a mixture model which estimates the means and the covariances for the different clusters in our data. In this case, we can then take the minimal Mahler-Nobis distance to any of these clusters. Let's try to understand the Mahler-Nobis distance a bit deeper. And for that, I claim that the Mahler-Nobis distance is actually equivalent to the surprise of a Gaussian. So how does that come to be? So assume we have a Gaussian which has the same covariance matrix and the same mean as we have used in the Mahler-Nobis distance. So then if we want to compute the surprise, then we have to take the negative log of the density function, which we do here. So we plug in the formula of the Gaussian and we arrive at this expression. Now it's just applying the log and then collecting all the constant terms into this constant c here. And we end up with something which already looks quite similar to the Mahler-Nobis distance. The only difference is that we got rid of the c, the multiplicative constant, and we applied the square root to the expression. But all of these are monotonous transformations, meaning that they won't change the relative ranking of the outliers in our data. So in this case, we can really say that this will give us the same result as computing the surprise of Gaussian. So in order to also get a practical grip on how to apply this, let's have an exercise. In this exercise, we are going to work through notebook number 1. If you have already opened the notebook, and then you will see that we start with a very simple exercise. So here we have prepared a synthetic data set, basically consisting of nominal data, which is one Gaussian blob that you see here, and anomalous data, which is like slightly off from the nominal data, but also in the shape of a Gaussian blob. And we want to apply the Mahler-Nobis distance as we've seen it before to this exercise. I hope that the individual tasks will be self-explanatory, and I would ask you to go through them on your own, and we will meet up together again to discuss the solution. All right, so I hope you all were able to solve the exercises. So let's see how the solution was intended. As I said, we want to apply the Mahler-Nobis distance to our data set, meaning that we need to estimate the covariance matrix and the mean. We do this in the following cell here by a very simple procedure where we make our lives a little bit easier by not fitting a full covariance matrix, but diagonal covariance matrix, meaning that we assume that the dimensions are actually independent in the data set, which is true since we know how the data was generated. So we can have a look at our result. We can see that the mean is pretty close to 0, and we have standard deviations of 1.3 and 1.7 in the two directions. If you compare this with the original distribution of the nominal data, then you will see that we are slightly off. Reason for that is that we actually fitted the covariance matrix and the mean on the full data set containing nominal data and anomalous data. Reason for that is that we want to assume that we were not able to identify the anomalies a priori, which is a very common setup, something that we have to live with in many situations, and we want to see how this affects our fitting procedures. So let us compare our fit against the true nominal distribution. Here you see the mean is centered at 0 or located directly at 0, and we have standard deviations of 1 and 1.5 in the two components. And again, we see the fit. Our contamination actually led to the fact that our mean is slightly off, so it's slightly up on the diagonal where the anomalous data resides, and also the standard deviations are slightly too high for our data, and we can definitely say that this is an effect that we got from anomalies in our data. So nevertheless, with our fitting procedure, we can compute Mahler-Nobis distances and then compute the ROC curve and the PR curve. So we see we have two very beautiful curves here. Both are close to being optimal. Remember that for the ROC curve, the optimal would be the edge having directly at 1.1, while for the PR curve, the closer we get to the opposite edge, the closer we are to the optimum. So now it's about choosing the right threshold for data set. And since we are only working with a two-dimensional data set, this can be done visually, or we can use visual inspection to aid our search. At this point, we could also go through all the possible thresholds and then compute the metrics, precision, recall, F1, and so on. But for the sake of intuitiveness, let's try to do this by hand and visually here. So this is our initial guess. We started with a threshold of 3. In the red line, you basically see the red outline shows the decision threshold. So everything that is in this circle will be detected to be nominal. Everything that's outside will be detected to be anomalous. This gives a rather good separation between nominal points and anomalous points, the precision being 0.6 and the recall being 0.9 with an overall F1 score of 0.72. Again, you can see that the precision tends to be relatively low, which is something that is not very uncommon in anomaly detection scenarios because of the high class imbalance that we have. As soon as we classify a few nominal points as anomalous, this will heavily hit the precision, and that's the reason why we have rather low values for precision. Often the recall is even more important. So very often, since anomalies can have high costs associated to them, you might want to detect all of them, and you can live with a few false positives in this case. But this heavily depends on the cost metrics that we've discussed previously. So by playing around with the value, we can also see how precision and recall are affected by the threshold. So let's choose a very low threshold and then compute the visualization again. So here I think you can very well see we have a terrible precision but a perfect recall. But actually most of the nominal data is now classified to be anomalous. So this is definitely too restrictive. Let's try what happens if we go to the other direction. Take a look. So now you see we have a perfect precision. Everything that we classify to be anomalous is actually anomalous. And even the recall seems to be not as highly affected as the precision in this direction. Nevertheless, as I said, we are actually working towards detecting all the anomalies, and we are pretty far off here. So this is really not an optimal value. So if you played around with this visualization a little bit, then you probably also came to the conclusion that something around to a 3.2, maybe a little less, maybe a little more, but something around this value should be rather good for our system. So what we can do now is we can take this threshold and then apply it to a new testing data set and see what happens. And maybe you were shocked when you saw the values, because you see that in this case, the evaluation is way worse than on our original training data. And this is due to a little trick that we used, because now we assume that we are in a case where we actually cannot assume that the anomaly distribution is really constant over time. So here we have actually moved the anomaly distribution a little bit closer to the nominal one, here at the 0.3. If we do a quick comparison with the original anomaly distribution, then you see it was the mean was at position 5.5. So we moved it a little bit closer. The adversarial tried to make his observations look a little bit more like nominal data. And we can see that this was rather successful because he managed about half of all the anomalous points remain undetected. And this is actually to sensitize you that this scenario where the anomaly distribution is really not well defined is a rather realistic one, and that there's a certain danger of using labeled data in order to assess possible threshold. Because we don't want to learn a specific anomaly distribution, but we want to be shielded against all possible anomalies that might occur. With these insights, let's continue with the course. I guess you have already noticed by now that anomaly detection as a whole does not seem to have really a common foundation. Rather, it seems to be more a loosely related collection of approaches and methods. And in the following, we want to try to categorize them in some sort of taxonomy. Because for the actual application, the structure of the data and the problem at hand is of extreme importance in order to choose the right method. It's even the case that sometimes hand-designed rules might work better than fancy algorithms. So a thorough statistical analysis should be performed before starting using heavier machinery. We will now walk through multiple philosophies that encompass multiple of our anomaly detection methods. So the first philosophy is the one of distance-based methods. Here we say that a point is an outlier if it has few close neighbors. Methods that imply this philosophy are k-nearest neighbor-based methods, clustering in combination with the Mahalanobis distance, the local outlier factor, or the matrix profile for time series. The next philosophy is the probabilistic one. In this case, we say most of the data is normal, and we can fit a probabilistic model of normality. And then a point is most likely anomalous if it has low probability under the fitted model. Examples of such methods are kernel density estimation, Gaussian mixture models, the extreme value theory, gun-based anomaly detection methods, or time series forecasting with probabilistic models. When looking at the first two philosophies, we can already see the blurry lines in the taxonomy. For instance, the Gaussian mixture model could be considered to be a distance-based method, especially when it's used in combination with the Mahalanobis distance, but equally well to be a probabilistic method. Subspace-based methods follow the philosophy that the space where the data lives can be partitioned into normal regions and abnormal regions. This partition might happen in lower or even higher dimensional subspaces. And common examples of such an approach are the isolation trees, which we will also see in this workshop. Another very popular approach are so-called reconstruction-based methods. The philosophy here is to first learn to compress the data, usually by mapping it into a lower dimensional space, then reconstructing the original input from this compression. Typical examples are autoencoders or their probabilistic variant variational autoencoders, associative memory models like Hopfield networks, or the principal component analysis. Again, we see the blurry line. PCA can equally well be counted as a probabilistic method. The same holds for the variational autoencoders. So finally, we have also supervised method. In this case, we don't use the unsupervised techniques that we've seen so far, but use typical supervised classifiers and use some additional tricks in order to deal with the data imbalances. There are, of course, many more methods, for instance, information theoretic methods, domain-specific methods, or even like ensembles of different methods. There's no way that we can approach all of these in this workshop. Instead, we will demonstrate a few techniques that are rather prototypical for the different philosophies and dive into two more specialized topics, namely time series analysis and extreme value theory. The techniques that we present are chosen so that they are useful in a variety of situations.